guys. Any questions about lab this week?
I have a question. When we're dumping our stuff and cleaning our glassware afterward, because we have organic and inorganic substances in our solutions, are we rinsing some of those with water and then acetone, or how are we dealing with those?
Are you asking what waste container to put it in and not the wash?
No, like how to wash it.
You would wash with both.
Okay, with water first, does it matter?
Basically, what are you trying to wash out?
That hasn't, because we have organic solids that we're putting, but we're putting acid and bases in some and then water in one.
You're probably going to wash with both. It's not a big deal. Do what you need to do. I don't see any other thing to tell you. If you got both, you're going to wash with both. You know what to wash with last.
The acid.
Okay, I think you're good. About the DQ page. So we got to be able to handle these line bond structures and what's formula of singular. Okay. I don't know if I know we did it at some point. It might have been the pre-course meet degree, but we got to make sure we know where carbons are, H's are at. Yeah. Had a couple of students who didn't seem to know where H's were at. And you got to be working on that. How many carbons here? This is a 6-member benzene ring. I see 6. Yeah. That's 6 there. 7, 8, 9, 10, 11. That's 6 more. Yeah. 17, 18, 19, 20, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. Hopefully I'm right. Is it C35? Somebody said no?
Some of them that did you? Okay. It looked like you counted some that had 4 already carbon, but
I was counting carbons. Is it 35 carbons?
Yes.
I can.
Okay. 35 carbons? Yeah. Thank you. H's. How many H's? How many H's on this carbon? 9. Carbon makes 4 bonds. Okay, I see 3 bonds here. The other bond is to an H. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 26, 28, 9, 30, 32, 34. Don't forget H's on heteroatoms. They're actually drawn in. 35, 36. Is that right? Okay. C35, H36. Then alphabetical. I see 1 chlorine. I mean, everything else is up there, right? What's next? Nitrogen. What we got? NO3. Is that right? Is that the right formula? Yeah, we do. Okay, you got to know where H's are at. All right, carbon makes 4 bonds. There's 3 H's here and 1 H on that carbon. There's none here because I see 4 bonds. All right. Any questions about line bond structures? You got to be able to. That's where we're going to show structures. All right. Yeah. What functional groups do you see?
Carboxylic acid, halide.
Carboxylic acid. You think? Yep.
Halide.
Alcohols. Aryl halide.
Aromatic rings.
Aromatic rings, yeah. This is kind of, you can call it an amine. It's kind of a heterocyclic. It kind of goes by a different name, but amine would work. Anything else?
Alcohol.
Sulfide, anything else?
Alcohol.
Alcohol. Okay, I see one other functional group that I would name.
Aromatic compound. Aromatic compounds.
I've already named aromatic. Alkene, right here, alkene. Note that carbon-carbon double bond in an aromatic is not called an alkene. But that carbon-carbon double bond is a classical, plain old alkene. Okay? Now you got alkyl groups, but they're so bland, they're almost just backbone. But they are an officially functional group, but they're, I just consider alkyl groups. You got two alkyl groups there. I mean, you got a cycloalkane there. We'll look at a little bit more later. DUS. Okay, we need to move ahead, but those are the questions you can be working on. I know some of you are asking during office hours, etc. We'll get to those as we can. Functional groups, DUS. We're looking at hybridization. Yeah. Back here on the bottom. Which bonds A through C can rotate? Can A bond rotate? Yes, it can. That is, this phenyl can actually be drawn up. Okay, just like my arm can rotate. My thumb is down, but if I rotate my arm, the thumb is up. Okay? That's a consequence of rotating.
So is that the B bond? Is that bond B that's rotating?
Let's look at the next one. Can B bond rotate?
No.
Yes, it can. A and B can both rotate. Can C rotate?
No.
Why can C not rotate? What?
It's pi bond.
C is a pi bond?
Oh, C is a sigma bond.
That was conjugation.
It's part of a ring.
Part of the
Who's got an answer? Can C rotate? Why not?
Because of the conjugation around the C, it has pi electrons because of that. Therefore, with pi electrons, it can't rotate.
Okay, I'm still not certain I understand your explanation because I don't see a pi bond there. Are you seeing a pi bond here?
No, but because
Well, that's where I thought you would say yes. There is pi bonding between here and here. Okay? Two p orbitals are overlapping. They're next door to each other. Okay? So that's why I'm unsure what you're actually trying to tell me there. I mean, you see a pi bond. I don't understand that. A pi bond, single bonds are sigma bonds, right?
Yes.
So is C a pi bond?
No.
That's what I thought you would say. No. Okay, since it's not a pi bond, can it rotate?
Yes.
Okay, but can this one rotate? Why can this one not rotate?
The p orbitals are open.
Because those electrons kind of move around in that ring, don't they? Like, they're not just stationed at those spots.
Okay, that's getting at, do you see a pi bond? You said no, but you're telling me you see a pi bond.
There's overlapping p orbitals.
Okay, there's some discussion there, and I can't understand your answer unless you're very specific about what you're saying. Because if you say something and I just don't answer you, then you're going to think you're right. Right? In the end, the reason C can't rotate is because it's in the ring. Okay? Look, here's a ring here. All right? Can this bond rotate? I just destroyed the ring. Okay, you see, that's the main reason it can't rotate. But there is some pi bonding between this carbon and this carbon because they both have p orbitals, and guess what? There are some interaction there. Okay? And that's what I'm trying to explain back there. That interaction there is some pi bonding. We'll get to that. That's aromatic. There's not a classical single pi bond up there. In the end, you need to know what type of bonds can rotate and what not. Certainly a bond in a ring can't rotate. You're going to just twist the ring and destroy it. Okay? Hybridization of each atom in Prozac, each heavy atom. What's hybridization of this oxygen here? This oxygen is
sp3.
No, it's sp2. Because anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. Didn't we say that? And we said that's a very important thing to know. All right? Don't we have a p orbital right here? Isn't that carbon over there sp2 with the p orbital?
Yeah.
Yes. So what is one of these lone pairs going to want to do?
Go to the p.
It's going to want to be in a p orbital. And for the only way to have a p orbital is for it to be sp2 for the p orbital. To graph the hybridization of that, so there's one electron over here. Every carbon in this ring has a p orbital. That's partly why it's called aromatic, right? Graph the hybridization of that oxygen. Okay, sp2. What type of bonds do you see the oxygen making? Single bond to carbon, single bond to carbon. What else do you see on that oxygen? Two lone pairs. One of them sits in a hybrid, the other one sits in a p orbital. This is a little bit incomplete, but that's enough. By the way, when I do something like this, you need to make sure you know what you're looking at, okay? I've already seen students who are looking at something and it's like, no, that doesn't apply to this. This was still over here. I'm not going to give you all these markers all the time. Make sure so when you look at it this afternoon or in 2 weeks, you're clear in your notes. Make sense? sp2, lone pair, and a p orbital. Why? Because there's one next door, and now these p orbitals can interact, and that's a good thing. If the lone pair was not in a p orbital, it would not be able to do that, and it would not be able to do it. A good thing. Question?
So if this oxygen has two pairs of lone pairs, why would the second pair not also be conjugated?
What lone pair, what p orbital is it going to interact with?
Could it not interact with the one that's a little further down?
Over here?
Yeah.
Well, that one's kind of far away.
What would
P orbital's on,
adjacent?
I mean, so p orbital there is going to interact with one over here?
Okay, so but if there was another, say, aromatic ring on the other side of the oxygen, would then the two lone pairs be conjugated by both sides?
You mean over here?
Yes.
No, because these three, now you'd have three conjugated. It's not going to do it. It's going to be one system.
So
Okay.
it's just going to be one.
It's going to be one system because if you want a second p orbital on this oxygen, how would it be positioned to the first one?
Still be, that would be.
It'd be perpendicular to the first one. That means this one over here would have to be perpendicular as well. You would end up with two like this and two like this, with the one in the middle having two. That's the two in the middle. And that's two different pi systems that are not interacting. It's best to have just three all interacting. The more you can have interacting, so it's not going to do it. If there was two p orbitals next door, then it might would do it. Just as a side note, that's about the 10th time some student has asked that question this week. And I'm not sure why, because in previous 100 semesters, I've had that question maybe one time. So I don't know if it's something I said or what, but that's interesting that you're asking the same question. It's a good question. I need to ask questions, think about, what do I need to know here? What are some possibilities? Can I explain possibilities? It's all good questions. It's just interesting that the questions being asked over and over at this point. Hybridization of the nitrogen over there. Good old sp3, right? The lone pair on the nitrogen is in what type of orbital?
SP orbital.
I just can't hear what you're saying.
SP
orbital.
SP3.
sp3, right? Okay. Graph the electron configuration of the nitrogen and the oxygen. We did the oxygen, nitrogen just sp3. All right? I mean, there's nothing there. It's sp3, you got 4 hybrids. You got 3 sigma bonds and a lone pair in those hybrids. Any questions about this page?
Professor, I'm not understanding when we have two lone pair, or I guess a lone pair in P, how it bonds with another orbital. I thought anytime we had bonding, it was only supposed to be one electron. Kind of like in what you have now, you have one electron and it bonds to the C. But then when we're doing the P orbitals, you have 2 electrons that are somehow bonding. Like, why is there not just one electron in the P orbital when you draw it?
More broadly, bonding is overlap of orbitals that contain electrons.
Right,
You're focusing on a traditional 2-electron covalent bond.
right.
but there can be other bonding. If you
Okay.
broaden that out to electrons and orbitals and the orbitals then overlapping.
So anytime for p orbitals to overlap, there can't be one electron, there has to be two electrons in that orbital.
No, it didn't say that. It didn't say it had to be two. In the example we're looking at, it's two.
Understood.
When I broadened it out, I just said electrons. I didn't say how many. Orbitals overlapping is going to be a bonding thing. You're kind of focusing on the traditional introductory two-electron covalent bond. There's a little bit more than that. Okay? Orbital overlap is a good thing until we get to organic 2 in a certain case where we can say it's a bad thing for a certain reason. All right? We haven't seen that yet. Right now we're seeing where this extra p orbital overlap is a good thing. It's called resonance. Okay? One day at a time, 1 week at a time. Kind of be open to it. We'll build upon it. Okay? Don't need to understand everything right now. Guess what? We don't even cover resonance officially until test 3. All right? Aromaticity. We don't cover aromaticity until middle of organic 2. But I gave you a definition there now because I want you to be able to recognize p orbitals. And we'll go from there. You with me?
Yes, sir.
All right. Good question. But remember, we're building. So take care of business today. Next week, this semester, we build. Okay, do you have any questions about that handout? I'll send out a answer key, I think, to the warm-up pages. Some cases I may not send out keys. I don't have them. Just consider them sort of extra questions. Or I could send you out a key to this and then at the same time send you some other questions that I don't give you a key to. The ultimate would be just to give you the test and not a key, and then you would have it. And so the more questions you have, it doesn't mean you have to have the key. All right? I give you plenty of questions, but I think I do have keys to these. Okay. Let's see where we're at. When I say we, I say, let me see where we're at. We're ready to move on to polarity of covalent bonds, I think. Any last questions about structure, hybridization, charge, anything like that outstanding? Functional groups? Question, yeah.
When there's a nitrogen in a ring and it has like a double bond on one side
Thank you.
and a single bond on the, is that an amine or is that not considered an amine?
As soon as you said the first word, I realized we need to look at that. In another regard, you're asking nomenclature. The one in singular had a nitrogen. Where is that? Warm up. No, singular. The EQ page, right?
Yeah.
Very important here. Very important nitrogen. This, you can call it an amine. It's called a heterocyclic amine. It's more often you're going to hear it called a pyridine ring. A six-member ring. If you take this and just put a nitrogen in it instead of CH, it's called pyridine instead of benzene. It's a pyridine nitrogen. It's kind of all the name it goes by. You can call it an amine. I really wouldn't call it an aniline. That's why I probably would never really ask you that. I would just kind of ignore it because it's not a name that we really need to know or can know at this point. It's more of an advanced name. But let's look at the hybridization of it. Can you graph the hybridization of this nitrogen? And importantly, what type of orbital is that lone pair in?
SP2.
Okay.
SP2.
Okay, I heard SP2, but I thought I heard something different here. No? I thought you said something, but I didn't. P orbital? Loud and proud. If you're wrong, then let's figure it out. I'd like to help you figure it out, but if I don't know what you're saying, I can't help you. The choices are either SP2 or P. It's SP2 hybridized. That nitrogen It's a traditional nitrogen. There's really no exception there. How many regions around it? Three. It's sp2. Okay, we have 3 hybrids and a p orbital. What type of bonds do you see that nitrogen making?
Double bond. Single bond.
Sigma bond to carbon, sigma bond to carbon,
Lone pair.
and pi bond to carbon. Right? And all together now, what's that there?
A double bond.
That's your double bond, and here's your single bond that we see. What else is on that nitrogen?
Lone pair.
Lone pair. And what type of orbital is the lone pair in?
sp2.
LP is in an sp2 orbital. Yes, not a p. The p orbital on that nitrogen is being used to make the pi bond that we see. Yeah? Standard nitrogen, very important where the lone pair is. Question?
I just still don't understand why the lone pair is
But you see a pi bond, right? How do you make pi bonds? Two different p orbitals. Okay? You want to draw this? You want to draw this? Trigonal planar, right? Trigonal planar is boom, boom. Does that look trigonal planar with 120 bond angles? Everything flat on the board? Yes. Over here is a carbon. Over here is a carbon, right? Nitrogen, 2 carbons. Nitrogen, 2 carbons. What's occupying this region? That's your lone pair, okay? This is an orbital. That's an orbital overlapping there and there. There's your trigonal planar. Right here. Sigma bond, lone pair. Trigonal planar. What else is on the nitrogen? P orbital. It's perpendicular to this. It's coming out of the board and going back. I can't draw it like that, but I'll just draw it like this. And what is it doing?
Bonding with the p orbital.
Next door, the carbon has a p orbital. It's like that too. 1 electron here, 1 electron here, and that's interacting to make a bond called a pi bond. So what do we have between the nitrogen and carbon?
A double bond.
A sigma and a pi, and we show that as a double bond. It's a sigma and a pi. And so the p orbital is being used to make the pi bond. The lone pair is sitting in the hybrid. This is hopefully shown with this. I like showing graphically. Help us see that and understand it. Did that answer it?
Yeah, so this only happens during the aromatic frequency.
No, it happens when the lone pair is next to the p orbital. Broaden your statement out. It doesn't have to be aromatic. We wrote the definition in the green sheet. It says it there. It said, it did not mention the word aromatic. All right? So it's an important type of nitrogen. When we get to acid-base chemistry, we'll state that a lone pair that's in a p orbital is not going to be basic. Because it's going to be busy conjugation. Doing conjugation, resonance. This lone pair is going to be slightly basic. Lone pairs and hybrids have some basicity. But that also depends on the exact hybridization. So you need to know where lone pairs are at, particularly for nitrogen, but really that applies to any atom. Because it's really the same question for any atom. So, important type of nitrogen there. Physical properties, I think we're ready to move on to. We'll have our first quiz on, let's say Monday, okay? We're dealing with lab next couple of days. First quiz on Monday, yeah? Okay, we have a 10-minute quiz first beginning of the class. We also want to spread out as much as possible, make use of the back row when we have quizzes and tests. All right? Okay, so structures. I call it the architecture of organic compounds. Functional groups, hybridization, bond angles, bond strengths, lengths. These are largely based on hybridization, types of orbitals being used. All right? Physical properties of organic compounds. Hugely important. Especially if you're going to start trying to work in lab with compounds, which we are doing this week with solubility. What color we got? Pink? Okay, some warm up there. You know, you get into drugs, pharmacy. Formulations of drugs, you know, how's it going to be administered? IV bags, you know, oral. Where's it going to go in the body? Does it have to get into the brain? If it does, it's got to pass the blood-brain barrier, which is very lipophilic. What does that mean? Okay, what type of compound can do that? Okay, the cell membrane is very lipophilic. You take the biology classes, look at the cell membranes, there's some structure there. Okay, there's some general terminology. So huge, lots of applications. Warm-ups there. Let's start with polarity of covalent bonds. Okay, an HH bond, very simple, will be a non-polar covalent bond. The two electrons are shared equally between the nuclei. Okay, equal distribution between the two hydrogen nuclei. HCl, on the other hand, the chlorine is much more electronegative. We know electronegative trend. All right? And so it's a little greedy. Yes, that is a 2-electron covalent bond. Can I illustrate with you? But it's not an equal sharing. Instead, it's like this. I don't want to break your arm off, but the chlorine is pulling, right? I like electrons. Of course, you know why that is. What?
Force of show.
Right, but why does it more electronegative mean? Why is it more electronegative?
It's closer to an octet.
It's what?
It's closer to an octet. It's trying to achieve an octet.
Okay, it has an octet. Just make sure you know why things are electronegative or electropositive. Okay, you do know a trend, but you also understand the trend, why it's like that. Chlorine's more electronegative, it's going to pool. Okay, so the electrons are more like that, kind of pool, okay? Covalent bond is not just sitting equally between the two nuclei. That leads to polarization because the electrons are kind of perturbed. They're not sort of equally distributed. All right, at this point we're kind of moving towards physics, and you talk about charge separation and induced charges and things like that. You ever heard that? Okay. Well, it's not induced, it's actually permanent because of the physical nature of the chlorine, the electronegativity. That leads to partial plus over here and partial minus over here. We also show that in the dipole arrow with so the plus end is showing the electrons are being pulled that way. I showed it here. So we call this a polar bond, and thus, well, it's only a one-bond molecule, so it's a polar molecule. Yeah? You have lots of polar bonds in organic chemistry. All around, just one of a million would be this one. Carbonyls are very polar. It's a double bond, but still it's, the oxygen's more electronegative, it's being pulled, okay? And instead of one arm, it's two being pulled, oxygen, okay? That's the only difference. Still we have partial minus, partial plus, and it's a polar carbonyl, like polarized group or bonding. I don't want to call it functional group, right? Because it's really not a functional group. Question?
If oxygen gains a partial negative and carbon becomes partial positive, then would hydrogen become even more positive because the carbon is positive, so the electrons go positive?
Good point. This polarization exists here, can influence the remainder of the molecule. So it's almost like tug of war. If I'm pulling here, I'm going to pull kind of all through there a little bit. The effect will tail off, but yes, it is beyond just the single bond we're looking at. We'll eventually get to there. Just intro here. This is an interhalogen, okay, which is more electronegative, the chlorine, so it pulls. The iodine is actually partial plus, okay. Very simple term we can say is the iodine is electrophilic. The iodine here is electrophilic because the chlorine is electronegative and it is pulling, making the iodine electrophilic. Which one's partial plus here?
Chlorine again.
It's the same thing, right? The bromine is partial plus, chlorine partial negative. So these are polar covalent molecules. What about things with more than one bond? I mean, that had more than one, but what about water? Two OHs, okay? Oxygen's more electronegative, pulling, leaving this partial plus, partial minus. What about over here? Same thing, partial plus, partial minus. But we have two bonds. They're actually equal, but there's two. What about the molecule as a whole? It has two polar bonds, but is the molecule as a whole polar? At this point, we have to understand that polarity is a vector, okay? It has a direction, and vectors can cancel, okay? Again, where'd you do vectors at?
Physics.
Physics or maybe a math, okay? Vector addition. Do these dipoles cancel?
Yeah.
They are equal, but are they exactly opposite?
No.
What's wrong with my structure?
Bent.
They look like they're equal and opposite.
It's supposed to be bent.
The molecule is bent, yes. Yes. We got to know the true geometry. In the true geometry, the molecule has a bond angle of 109.5 here. Okay, it's not linear, it's more like this. And so this is like this, and this is like this. Okay? And these actually add up to a single molecular dipole moment, it's called, that is going to, if you add these together, you're going to get one dipole that's sort of right up the gut here. Okay? Molecular dipole moment illustrated here. So we have to add the vectors together. And since it does have a MDM here, we call it a polar molecule. So you got to know geometry. We'll do some examples there. What do we have here? Down the road, this will become an important type of compound. We have dipole carbon and bromine. And so this carbon has partial plus as a result of the bromine. Up there as a result of the oxygen. These carbons are said to be electrophilic. Okay. All right. Now that's not a formal charge, okay? Not a formal charge. It's a partial charge. Covalent molecules, vector sum. We've already done water. We did water above. Okay. What about CO2? You're going to have to put together a structure. Okay. Hopefully you can put together a structure, CO2, with carbon being the central atom. It's the most typical structure. I'll draw structure here. I won't worry about bonding those, right? Let's just put something up here. Is that a good structure for CO2? Okay. Carbon 4 bonds. Oxygen 2 bonds, 2 lone pairs. Yeah, that's classical structure for CO2, carbon dioxide. Is it a polar or non-polar covalent molecule?
Non-polar.
You'll see in the O, I have dipole here. Also have dipole here. Are these equal? Yes. Are they exactly opposite?
Yes.
Is my geometry right around the carbon?
Yes.
It is sp. Could you graph the hybridization of that carbon real quick? It's sp. It has 2 regions around it. That's sp, right? How many p orbitals? 2. What type of bonds do you see?
2 sigma.
Sigma bond to carbon, right? What else do you see?
2 pi.
Pi bond to carbon, right? What is this? That's one double bond to, I'm sorry, we're not bonding to carbon, we're bonding to oxygen. Oxygen. Sigma bond to oxygen, sigma bond to oxygen. That's one double bond to oxygen, that's the other double bond to oxygen, yeah? Hybrids set the geometry, 2 hybrids are going to be linear. It's going backwards. We started with the idea of linear, so we showed two diagrams. Question?
Wouldn't the pure orbitals have enough high bond oxygen as carbon?
That's obvious.
Everything's oxygen. Sorry.
Oh.
Used to doing everything's oxygen. Okay, so we got there. Yeah, it's nonpolar. Okay, the dipoles are equal because they're both CO. But they're also exactly opposite, so they're canceling each other out. What's the consequence of this? Now, actually, there is partial charges here. This is partial minus, that's partial plus. Does that mean the compound is polar?
No, there's no net dipole.
Hmm?
There's no net dipole.
There's no net dipole.
So
What's the consequence of this? Why do we want to ask this question? If it's polar or not?
Solubility.
Solubility. Okay. There's some vagaries with that because it does have a partial minus in that could interact with a partial positive of something else. And so, what does it really mean to be nonpolar? What does it mean in physics to be nonpolar or polar? I think one consequence of this, if you put this into an electric field, okay, here's a molecule of CO2 floating in an electric field, okay, is it going to respond to the electric field?
No.
I think it would not respond, would it?
No.
If it was polar, it would maybe experience a torque because it would line up with the electric field in some way because the electric field has polarity, doesn't it?
Yes.
And so it would go boop, and the molecule will experience a torque as a result of it being polar. This ain't going to torque. Because if the minus is up here, which minus end is going to, if the positive is up here of your field, which minus end is going to torque up towards it? Both ends are minus. Why would this end torque up if the other one is? And so it negates each other and it just sits there. And if it just sits there, we say, hey, it's not responding, it must be nonpolar. That's a physics look at it. Here we can look at the structure and tell it's nonpolar. Okay? So, taking your information from other science disciplines and sort of, okay, how does this go together? All right, so what are the consequences of polarity? There we go. You try the rest on your own and we'll hopefully look at those at some point. All right? You got to have good structure, right? Because structure tells you if things are really cancelling. Structure. All right. Now then we get to ionics. Ionics is sort of the maximum of polarity. Like if we had a sodium chlorine bonded together. First off, you would never do this. We learned in Gen Chem that sodium is always ionic, right? Okay. But if it was, what type of difference of polarity would you have here? A huge difference. And instead of the chlorine just sort of acting greedy, the chlorine goes, sorry, ripped your arm off. I'm so greedy, I took your electrons, and these electrons, this is a mechanism here where we can show them just moving on to chlorine as the fourth lone pair. And now we have ions because that chlorine is now minus and the sodium is now plus and it's ionic. Okay? It never was this. This is how it exists because you just have such extreme difference in electronegativity. And when the molecule was first formed, this is how it formed. It formed as an ion. Right? We call it an ion pair because it is a pair of ions. Colloquially, we call an ion pair a salt, right? Okay? And sodium chloride is the most common salt, table salt, but there's many other salts. Potassium iodide is a salt. Sodium phosphate is a salt. Any ionic pair is a salt. So that's the extreme of ionic. Physical properties. Guess what? We'll probably come back and touch on some of that intro information as we build upon it. Physical properties. Too many things we'll look at. Boiling point and melting point, which sort of go together. And then solubility, which is our lab this week. For something to boil, okay, Okay, you are all individual molecules, okay? If I'm going to get you guys to boil, first off, if you're kind of hanging out, molecules are doing what with each other? They're interacting, okay? We got a pinky bond here, we got elbow, we got arms locked over here, okay? We're interacting somehow, all right? And that leads to it being liquid or solid, depending on how those interactions are, all right? If it's a lot of interactions, it's fixed and it's going to be solid, okay? If the interactions are more weaker, then things can sort of move around a little bit and it's liquid. If we're going to get the liquid to go to a gas, what do we have to do for these interactions? You got to break them and say, okay, everybody separate and let's go off and be a gas. We have to overcome these, what type of interactions?
Intermolecular forces.
Intermolecular forces. That's the official term, IMLs. You can also call them non-covalent interactions. Okay? Because these aren't covalent bonds. They're non-covalent interactions. Right, so that's terminology. So in both cases, we have to sort of look at IMFs. In general, the more intermolecular attraction, the higher the boiling point. Right? The more you guys are hugging on each other and doing all this, the harder it is for me to get you to boil. The more energy I'm going to have to put in. More energy means higher temperature to get you to boil, higher boiling point. Importantly though, what are the main types of IMFs? They are listed here, 4 of them. We will go through each 4. First one being van der Waals attractions. That is the weakest. These are in order. 4 would be your strongest. Van der Waals, which I call it that name, sometimes you hear other names like London forces, dispersion forces. I kind of consider it all the same. There are subtle differences, but I'm not going to get into subtle differences. I'll illustrate it with some examples here. Look at this trend. These 3 hydrocarbons, right? These are just hydrocarbons. These 3 alkanes, everybody agree these are just alkanes? Saturated, everybody agree those 2 are saturated? Okay, so we have terminology that we've been developing, yeah? Okay, so let's look at the trend of these 3 saturated alkanes, or hydrocarbons. This one's a gas at room temperature, boiling point here. The boiling point's higher, it's actually a liquid at room temperature. Then the boiling point gets low again. Here, why is this one higher than this one? Well, you could be kind of cute and say, well, it has greater IMFs. Obviously, that's why the boiling point's higher. But we need to explain more. What type of IMF does it have? Well, you can be cute and say, since it's number 1, the answer is van der Waals attraction. But then I would say, well, what does that mean? Okay. Van der Waals is the weakest. It's a fleeting dipoles, temporary induced dipoles. It turns out when molecules approach each other, I'm a molecule, you're a molecule. When we approach, what's on the skin or outside of a molecule? Electrons. The electrons come in contact with each other and they kind of get perturbed. All right? And that perturbation or movement leads to temporary dipoles. In physics, I think you induce this by rubbing a balloon or something and it sticks. Because the rubbing leads to the electrons being perturbed more. And it leads to temporary dipoles that are strong enough to have an effect. And I'm kind of showing this. These are rubbing up against each other, and these temporary dipoles are created. The take home here, though, the bigger the molecule is, the more surface area it is, and the more temporary dipoles you get, and the effect becomes bigger and bigger. Now, I call it temporary, but if the molecules are confined together, the temporary is going to be sort of ongoing. Temporary it's not an actual permanent dipole. Because if you look here, do you have any dipole here in any of these bonds? By the way, we didn't mention here, a CH bond is not considered polar. There is a difference in electronegativity between the 2 atoms, but CH we consider non-polar. All right? There's no dipole there, but there is possibility of temporary induced dipole, and the larger the molecule, the more that you get. So we say that this actually has higher IMFs because of so-called van der Waals attraction. And so this phenomenon is significant enough to lead to this having basically a 40-degree higher boiling point. Why does this one over here go lower? Because in terms of, that's C3H what? Real quick, C3H8, right? Because it's saturated, 2N plus 2 is 8. This is what? C5H12, good. This is also C5H12. These two are what? Constitutional isomers. Yes. Why does that isomer on the right have a lower boiling point than this one?
Less surface area.
Because it has less surface area. Because here, the center carbon is actually hit in the middle, and it doesn't contribute to the surface area. The take home here is branching does what to boiling points typically?
Increases.
It decreases, because branching lowers surface area. Less surface area is going to have lower boiling point. That's why it went down. It's actually a gas at room temperature because it's less than like 22. Is that room temperature? Approximately. Branching lowers, all right? A branched hydrocarbon there. Yeah? Good with van der Waals? Number 2 is what? Dipole, dipole. Here we have compounds that actually have a permanent dipole. Right? Partial plus, partial minus. Partial plus, partial minus. Does this have a permanent dipole?
No.
No. These two, because they have permanent dipoles, it's a stronger dipole. It's not induced. Induced is weaker. This is a permanent. It's stronger. Because it's stronger, it's stickier. Okay? Here I am. Here's the minus part of my body, and here's the plus. Okay? Oh, a plus. Ooh. I'm attracted to that over there. Lots of attraction. Permanent. Larger. Here I'm showing sort of the IMFs. Partial minus of the oxygen being attracted to the partial positive of another molecule, the carbon. And we show the non-covalent interaction, or the IMF, intermolecular force, or intermolecular attraction. Is it IMF or IMF, right? I'd rather call it attraction. But we show it with a dash, okay? Really, I want to call it a non-covalent interaction. I think that's the best term to use for that. The dashed sort of interaction, illustrating the dashed bond. Right? So all these molecules are sticking together because the positive end of one is being attracted to the negative end of another. We'll pick up here. Need to move through hydrogen bonding. Very important. Solubility. We'll be moving into that as we move into it in the lab. And then after this handout, acid-base. Please be looking ahead at acid-base.